My name is Tyler Labonte, and on behalf of my co-authors John C. Hill, Zinchen Zhang, Vidya Muthukumar, and Abhishek Kumar, I will be presenting our NeurIPS 2024 paper, The Group Robustness is in the Details, Revisiting Fine-Tuning Under Spurious Correlations. Deep neural networks are susceptible to spurious correlations, patterns which are predictive of the target label in the training dataset, but irrelevant to the true labeling function. These spurious correlations cause the model to have poor performance on data where the correlation does not hold. To formalize this phenomenon, we partition the dataset into groups, which are formed by the Cartesian product of the class labels and the spurious features. Our objective is to maximize the worst group accuracy, or the minimum accuracy on any group. This is particularly important to ensure good performance on minority groups, which may be underrepresented in the training dataset. A popular and lightweight method to improve group robustness is class balancing. The key idea is that groups are subsets of classes. So if we ensure the dataset has equal numbers of data from each class, we will implicitly partially balance the groups, which is known to improve worst group accuracy. This method is easy to implement and does not require expensive or private group annotations. Below, we provide an example of how class balancing, or ensuring equal numbers of land birds and water birds in the dataset, contributes to group balance. In our work, we re-examine the nuanced behaviors of class balancing in conjunction with model fine-tuning from a pre-trained checkpoint. Our three contributions are: first, we identify two failure modes of popular class balancing implementations, one catastrophic. Second, we show that model scaling benefits group robustness only in conjunction with appropriate class balancing, and it can even harm robustness otherwise. Third, we show that group-wise spectral imbalance can still harm worst group accuracy even under appropriate class balancing. Crucially, we investigate three popular class balancing implementations and show that even though they are theoretically proven to be equivalent in the population setting, practice looks much different. The first method is subsetting, where one removes data uniformly at random to train on a fixed class balance subset. The second is upsampling, where one adjusts the sampling probabilities so that the mini batches are class balanced in expectation. The third method is upweighting, where the losses on minority class data are scaled by the class imbalance ratio. We find that class-balanced upsampling and upweighting induce a catastrophic collapse of worst group accuracy over the course of training. One can see that the purple and green lines in this image converge to the blue line at the end of training, which is equivalent to the performance using no class balancing at all. Moreover, we uncover a previously unknown disadvantage of class-balanced subsetting. Even though it performs well in Celebes and civil commons, on waterbirds, subsetting is the worst method by far. This is because waterbirds has a small minority group within the majority class. So when the majority class is cut with subsetting, the small minority group greatly suffers. To rectify this, we propose a new class balancing method called mixture balancing, which interpolates between subsetting and upsampling. Mixture balancing greatly rectifies the catastrophic collapse of class balancing methods in all three datasets. Next, we study the practically relevant setting of scaling the number of parameters used for fine-tuning a pre-trained model checkpoint. We find that model scaling improves group robustness only with appropriate class balancing and can even harm robustness otherwise. We note that the last dataset here, multi-NLI, is class balanced a priori. Finally, we investigate the eigenvalue spectrum of the group covariance matrices, and we find that a spectral imbalance exists even under appropriate class balancing. In particular, while the worst group may not have the largest spectral norm, the minority groups consistently have larger eigenvalues once conditioned on the classes. This may contribute to a group disparity despite balanced classes.